Welcome 2100. We are back and we're doing uniform circular motion today. Now, this is our equipment that we'll be using. Your lab manual goes into it quite well. The details, how it works, what we're supposed to do. Read your lab manual. Read it twice, in fact. Make sure you fully understand it. At this point, you would have received a lecture from your lab instructor. You would have read your lab manual. You know what we're supposed to do. So let's just jump right into it. Right now I'm looking at page 36 of the lab manual, and in bold there it says the specific steps for prepping the setup are, and then it goes into some bullet points there. First one is to disconnect this bob. Now, we are going to get this in motion. We want it traveling in a circular path, and obviously the center of that circle is going to be right through the axis of this rod here. But we can control the radius of that circular path. All we need to do is just pick one value. It's going to remain constant throughout all of our runs. We just need to pick it and make sure that we spin this in such a way that this bob is always at that particular radius that we've chosen. So in this case, we'll pick 18. Your lab manual states that there are some cogs that pertain to different distances, and what those cogs are these little guys right here. I don't know if you can see them. That doesn't matter if you can't. They're just little bumps here, and each one of those pertains to a certain radius. Now, the one we picked was 18, so that pertains to this one here. And they're spaced out 1 centimeter apart, so there's some leeway with which radius you want to choose. Like I said, we'll pick 18, and when we spin this, we always want to make sure that this bob is directly above that 18 centimeter cog. So how do we go about doing this? Well, I guess this was designed in such a way that the person spinning it would place his head like right here and watch as he spins it, so that the tip of that bob always passes over that cog that pertains to the 18 centimeters. What we do in the lab sometimes is put a little piece of tape on that cog that we've chosen, and that little piece of tape sticks out, and the bob, manufactured in the way that it was, it has a little tip on the bottom. So as that cog, as the bob passes the cog, the tip of the bob hits the tape. So that ensures us that we are always at that chosen radius. You hear a little click, click, click as you're spinning this. Now, I was going to go about doing this that way, and the viewer would time the period as this bob travels along that circular path. But the problem is that I don't know if you will really be able to hear this bob hit the tape. So anyway, I want to make this as easy as possible for you so that you can get good results. So I'm going to do it in, well, a slightly different fashion. But bottom line, the important thing to realize is we are choosing 18. Let's see. The next thing we're supposed to do is take this bob off and measure its mass. So I'm not going to do that right now. We'll do it later. We don't need that for the experiment. We need that for analysis. So that'll be like the last thing that we do. We'll take the mass of this bob. We are also, let's see. Well, actually, that's about it. I may as well just tell you now how you will go about timing this. As this is spinning around, it's fair to say that if I spin it too fast, it is going to overshoot the 18 centimeter mark. If I'm not spinning this fast enough, it isn't going to quite reach 18 centimeters. After all, this spring is going to be attached to this bob. So this is how one, will know that we are at the correct radius, and two, this is how you'll know when to start and stop the clock when you're timing this. So this is a reflective surface. What I did was I just threw some black electrical tape on the bottom here so that just a tiny piece of this tip is showing or is reflective. And what I'll go ahead and do is shine a laser such that whenever this is directly over that 18 centimeter cog, the laser will reflect off the tip of the bob. So you'll be watching me spin this, and when you see that flash of light, that's when you know that it has made one complete turn, or that's a complete cycle. Let's see. In fact, let me put you on pause and show you what that looks like before we start spinning this. Okay, hold on. Okay, so we are in the dark, and I turned the lights off just so I could illustrate this point more clearly. Here's our bob, and when I place the bob over the 18 centimeter cog, this is what you'll see. See that little light there? So we know that every time it passes that that cog, you'll see a little flash of light. Now, let me see if I can get this thing spinning, and I'm not going to try and do it with any great degree of accuracy. This is just to illustrate what you'll be seeing when we actually do the run. But if you just focus on the portion of the equipment that has the cog, you will, of course, see that little red light. And that light is going to serve, like I said, two purposes. One, it'll ensure me, the spinner, that I'm spinning it at the correct speed. Second, and most importantly, it will tell you when to start and stop the clock. Now, let me turn the lights back on. The author instructs us to do this like 20 to 30 times. 20 sounds good to me. So when we end up doing this, oh, the other thing is, he suggests that whenever the bob passes this cog, you count, but you start at -3. In other words, this thing is spinning, and you'd go like -3, -2, -1, 0, 1, 2, 3. And the reason for that is that the individual responsible for timing this motion kind of gets a sense of how quickly it's making its rounds. So it's -3, -2, -1, 0, 1, 2, 3. It's important that you start the clock at 0, right? Or else when all is said and done, you're going to be missing one period and you're going to get bad data. So that's how you will time this. And let's see, we're going to do it 5 times. We're going to put different tension on this spring here so that we can examine this motion with 5 different forces exerted on this bob here. So there are 5 different holes. When we start doing this experiment, I'll probably put like a little post-it here with the number. And that number doesn't serve any purpose as far as a measurement. I'm just enumerating the holes in the ladder. So it'll be like hole 1, hole 2, hole 3, 4, and 5. And that'll help, well, both of us. When I'm editing all this together, I'll see a video that has a post-it on it, and I'll know which, I'll know how much tension was on the spring. And you'll know which, you'll be able to differentiate these different runs. So let's see, that is about it, and let's get started with run number 1. I'll put you on pause. Hey there, guys. I already recorded video of me spinning this with the 5 different tensions on that spring. But what I'm doing is, well, I failed to mention something. Now, when you're in the lab and you have a little piece of tape over one of those cogs and you're listening for this bob to hit it, sometimes what happens, or I should say often, when you're spinning it, you'll miss it, especially if the number of periods that you're timing is a large number like 20. Out of those 20 cycles, there inevitably is going to be a few that you're going to miss. And what happens is that it's suggested that you don't pay attention to that. You just act as if it did. So that's what I did in my video. I never miss more than one, but you'll notice for a particular trial, there may be a time when this passed the cog, but you didn't see the light, and that's just because I wasn't spinning it at the correct speed. It's funny because so that was happening, and I'd immediately stop, delete the video, and then re-record again. I have this problem with like everything has to be perfect, right? And it doesn't make any sense because I mean that's ultimately the reason why we do a large number of ends, a large number of periods, so that when we determine the length of one period, it all averages out, you know, the errors. In other words, on some of those passages of the cog, I may not have been spinning it fast enough, so it's slightly below it. You still see a light, but it's slightly below it. And then other times, maybe it's just a little bit too fast. You still see the light, but it's slightly above it. And then sometimes it's a couple of millimeters off your mark, so you don't see the light at all, but it all averages out. So I just went ahead and started leaving those clips in if I missed one. So you may see this travel around the cog, and I'll call out the number. You won't see the light off the laser, but just act as if you did. And let's see, this pretty much goes without saying, but as I'm counting, like, you know, the -3, -2, -1, 0, 1, don't start and stop the clock based on my voice. I mean, this is obvious, right? The laser, you seeing that red mark, is going to determine when you start and stop the clock. I'm, of course, am just counting the period so that I know which one I'm on, and you know which one I'm on, so that you know when it's coming up to get ready to look for that red mark and turn it off. And of course, well, this is all self-explanatory, right? I'm sure you're going to get great results. In fact, what I will do is analyze this data as well. And well, I always do anyway. If something, if we have bad data, I'll correct the problem and then just reshoot it. But it hasn't happened in the past with any of these other videos. The data's always good. But this is just a new method. We've never used a laser in class. I'm just doing this for your benefit. So get ready to time your first run. That will be ladder position 1. And I'll put you on pause and see you in a minute. Okay, right now I'm just gaining practice. I'm trying to get a sense of how much force I should put, or torque I should say, on the tip of this rod. And I seem to have gotten the hang of it now. Almost, kinda. Okay, anyway, let's start timing shortly. What I'll do is I'll start counting for you. Okay, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There you go. Okay, quick recap. Now, we got this bob spinning with uniform circular motion, and well, what was responsible for causing this bob to travel in such a fashion? It was the force exerted on this bob by that spring. Now, we are going to determine what that force is. We're going to do it two ways. First, of course, is in a theoretical fashion. Now, according to theory, what is that force equal to? Now, what is it? 4 pi squared times mass, the mass of the bob, times r, radius of the circular path, times the frequency squared. So I'll give you the mass later. What we need is f, the frequency. Well, we just figured out what the period is, right? So you could determine the frequency. It's just the inverse, right? So that's how you will theoretically determine the force causing that motion. Now, we are going to attempt to validate that. And how do we do that? We will directly measure that force, and here's how we go about doing that. Right now, this is on the first hole of the ladder. What I'm going to do is, I have a hook with weights on the other end of the string. Now I'm going to attach it to this bob, and let me set it, let me set it in motion just a bit, just so I can get rid of the tension in that pulley there. And the tip of that bob is right over our cog. Now, I really drove it into your head, the whole 18 centimeter, the radius of the circular path being 18 centimeters. So when I set up the laser to do the runs, I ended up setting it up inadvertently over the 19 centimeter cog. So you haven't done any analysis, nor harm nor foul. 19 centimeters, and I'm going to keep mentioning this just so you get it in your head. Our R is indeed 19 centimeters. By the way, let's make it 19.0 centimeters. By the way, we timed it. I'm considering error right now. I would say that this could be off by up to 2 millimeters. So by the way that laser was shining on the tip of that bob, we could be off up to 2 centimeters. So that will be your error, not that you're supposed to determine error in your final analysis. But if you were, or if your instructor has you do that, the error in this particular measurement is plus or minus 0.2 centimeters. But anyway, we are at 19. Our R is 19.0 centimeters, and I hung some weight on this bob now, getting back to originally the point of finding our force through a method where we're directly measuring it. So this isn't theoretical, it's just a direct measurement. I put enough weight so that this bob is directly over the 19.0 centimeter cog that it was traveling over as we calculated our period. So I know now how much force was exerted on that bob during the motion, because I've stretched that spring out the same distance. And no, I didn't just get lucky. I played around with weights prior to videotaping this, and that's how I was able to just throw the hook on, and it's perfect. So this much weight was responsible for stretching that string the same amount as when we were spinning it around. So What is the force? What is our measured force on that spring for that particular one? It's nothing more than this mass times G. $305.8 grams. 305.8. And by the way, if you're wondering why this can is here, it's so that you won't be distracted by that laser dot on the wall while I'm spinning it. You'll just, anytime you see the laser, it'll just be when it hits the end of the bob. You won't see it being reflected off that wall. But anyway, we are just about done. I mean, yeah, you're going to see, you're going to time this again 4 more times. We are going to, after each run, determine what we're going to measure the force on that spring by hanging weights on that hook. But there's really going to be no explanation of what's going on. You got it, we're good, and we're just going to knock it out. So let me put you on pause. Okay, let me just get some practice here. That looks about good. It's funny, when I start counting though, that's when it messes me up. What, I can't do 2 things at the same time? All right, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so here is the system configured so that the spring is in hole number 2. Now, there is no weight on the bob. I'm holding the weight with my hand. Now let me release it. Let me get this moving back and forth a bit, and that's just to relieve any frictional forces in the pulley. And you could see that the bob is directly over the 19.0 centimeter mark, and we're good to go. So let me determine this weight. Actually, I already did. I already weighed it. 431.0. 431.0 grams. Okay, let me put you on pause and we'll get to run number 3. Okay. It's getting harder, but that's about enough practice for me. See, I already missed one. Okay. It is getting harder. I'm just practicing. So let's start shortly. -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, what was the force exerted on that bob from the spring during the run with hole number 3? That's the spring unstretched. And when I put the weight, I like to move it just to be sure. There you go. The bob is right under that 19.0 centimeter cog. And I'll weigh this. Oh, I already did. Forgot again. It is 540.7 grams. Okay. Ready for the next run. Again, just getting some practice. Okay. See, I messed up. Okay, just trying to get some practice, and we'll start shortly. -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. Moving right along, we are now at hole number 4. That is with no weight on the bob, and that is with weight on the bob. It is coming to rest, and indeed the bob is directly over the cog of interest. Now, which cog is that? The one that pertains to an R of 19.0 centimeters. And let's see, I already determined the mass that is hanging on this hook. It is 650.5 grams. All right, get ready for your final run. Okay, right when I think I got it, I mess up. So let's see how this goes. All right, just a second. -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Cool. Okay, so this is the last direct measurement of the force. This is on hole number 5. That is the unstretched spring. And here we go. That bob is directly over the 19.0 centimeter mark. This is quite heavy now, as you can see. And this weight is 770.2 grams. Now, one of the first things that we're supposed to do is determine the mass of this bob. And remember, we did not do that. So we will do that now. Here we go. $365.3. Let me write that down for my records. 365.3 grams. Let me put you on pause for a second. Yeah, we're all done. Good luck on your analysis. In fact, I'm going to do the same right now. Make a graph and make sure that, well, this data is meaningful. It's good stuff. I just want to make sure that you will be able to, if analysis is done correctly, get a minimal amount of error. So have fun doing that, and I will see you next week.